So hi everyone, let's start. So today I owe you two things. So the first thing is to complete the characterization of the places of the rational function field. We started last time, and actually we analyzed all the places phi from kt to some field L plus infinity, in which phi of t not infinity. So I will repeat quickly. And then there is one more case, one more place, the case of in which phi t is infinity. So we will see that this gives rise to one more place, the place of infinity that we saw today in the lecture. And then we will prove the lemma of the indexes that we also used today twice, I think. So that's the plan. So let's have a quick recap. So we have the simplest function field, the rational function field, kt over k, and we have some place phi from kt to L and infinity, where L is some field. And so remember, a place is just a place of a function field. It's a place such that it is non-trivial on kt and trivial on k. And last time we showed that in this case, if phi of t is not infinity, then let's say that it's some value tau in L, then we showed that there exists a unique monic irreducible polynomial p of t, such that what is the place? Well, if you give me a function in kt, we simply write it as, so it's a quotient of two polynomials. We can factor the numerator and the denominator, take all the factors of t, and okay, so last time we showed where this p comes from, but so I won't repeat it. You can find it in the notes. So and then once we have this p, it was the generator of the kernel of something. Then any function we can write as p to the n times f of g, where f and g are coprime, and p does not define neither f nor g. And then if the three cases, if m is positive, then it's 0. If m is negative, then it's infinity. And if it's 0, it's just f of tau over g. So maybe I will say, so this p, where did it come from? So we said that if phi of t is some not infinity, then we can consider the restriction of phi to the polynomial ring. And then if t is mapped to tau, then every polynomial in t is mapped to some value in L. And then we have a ring homomorphism phi restricted to the polynomial ring, from the polynomial ring to L. And its kernel is a prime ideal of the polynomial ring, and P is the generator of the kernel. So since the kernel is prime, P is reducible, and if we normalize it, we can assume that it is monic. So there is a unique monic. Okay, so two things that I will leave it to you to check. So the first thing is that indeed every prime, okay, so I mentioned that there is a one-to-one correspondence between the places which satisfy this condition and the monic irreducible polynomials in kt. So we saw one direction that if we have such a place, then it corresponds to some polynomial. And conversely, if you start with a polynomial, you can find, there is an associated place that is induced by this p. So I will upload the notes today, and then I will elaborate a bit more about this. So indeed, there is a one-to-one correspondence between the monically reducible polynomials in kt and the places of kt over k such that phi of t is non-infinite. So two things to check. First is easy, that for distinct P1 and P2, we get places which are not equivalent. So, okay, that's easy. I think we already saw it in the lecture. So, and the second thing is what is the residue field of this place. So the residue field is, today we use the fact that the residue field is a finite extension of k, of phi of k, isomorphic. And so exercise and show. So last time we also described the corresponding valuation ring and the valuation and the maximal ideal. So all this we did last time. And the one thing we didn't was what is the residue field of this thing. Yes. So show that the residue field, so let's call it phi of OP is isomorphic to this. So the residue field is like the subfield of L. It's just the image of phi when we omit the infinity. And in this case, I claim that it is just isomorphic to this field extension. And this is indeed a field extension of K of degree degp. So it's a good exercise. Okay. OP is just all the elements here that are not mapped to infinity. So it's the same way to define that.
All the elements with variation and non-negative?
Exactly, and it's the same. The valuation is
just in this case, because the negative valuation not to infinity.
An element is in OP if and only if its valuation is non-negative. It is defined. It's not written infinity.
Yes, but what about an element is mapped to infinity if and only if valuation is negative? That isn't.
Yes, it is. So the valuation is just like what is the order of the zero of our pole. So if it is a pole, then it must be negative, at -1 or less. Okay.
So this is OP for like the valuation that comes from P, which
is
M.
Right, for this place associated to this P.
So it's OP of V of P, which when V of P is M in this case, right?
Right, V of P is B, exactly. V of P of U, if this is U, is just M. Yeah. And yeah, that's, so last time we discussed all this. So let's complete it. The second option, which is easier, is the case in which phi of P is infinity. And then what can we say about phi of the inverse?
Zero.
Exactly. So it follows easily from the definition of a place. So now suppose we have an element U. So let U and some non-zero rational function. Then how can we evaluate? Just write it as right. U as say quotient of two polynomials, where AK and BL are non-zero. So any non-zero rational function is a quotient of the polynomials, say of degree K and degree L. And then what can we do? We can factor T out, take T to the K out of the numerator and T to the L the denominator, so we get T K minus L times, so times what? So here we get AK plus, okay, it's just a calculation, so you can ask me or check, plus A0 T to the minus 1 the K over BL plus BL minus 1 T minus 1 plus B0 T to the L. Just taking T to the K out of here and T to the L out of here. Okay, and what can we say about this term? Right, and if phi is a place, where it has to be mapped. So, right, so if we only consider without this, only considering this, right, so T to the minus 1 has to go to 0, and since everything is nice, so phi of this is phi of this over phi of this. Phi of this is just phi of AK, phi of BL, and all the rest are 0. So in other words, phi of this term is just AK. Oh, we even know that without loss of generality, phi is the identity on K. So all these coefficients are in, all the AIs and BIs are in K, so phi maps them to themselves. So we just AK over BL. Okay. So in general, what is phi of U? So remains only to consider this thing. So we again split two cases. So if K and L are equal, then this is 1. So what is the value of phi of U? Phi. And if K is larger than L, exactly. So K is larger, the T is to some positive, so it's infinity. 0.
Sides with the
So
coincides with the calculus. I mean,
oh, so good. So what is, let's say, so what is the valuation rate? So this is a, so there is only one place without loss of generality, this one. And what is the residue field? So the values which are not infinity are either 0 or a quotient of some two numbers in K. So it's in K. So the residue field is just K.
So when you say that like this maps to 1, like we can, why does P maps this to AK over BL and not like some constant?
Oh, so here, so all the terms that in which t to the minus 1
These are
appears
zero.
are 0. So it's phi of AK over phi of BK,
Yeah.
ABL, and without loss of generality, phi is the identity on K. We saw that last time.
So okay.
So we may assume that phi of AK is AK and phi of BK. It's
When
just
you say not generality, you mean like there's someone which is like another field which is equivalent. It's the same.
right. So if you remember, today we have F, we have K, and we have phi, L, and the infinity, and then K is mapped to some. It's trivial on K, so it's not going to infinity. It's going to only a subset of L, phi of K, and these two are isomorphic. Since phi is injective and onto, so we under this identification, it maps every element in K to itself.
Okay.
Yeah.
Under there's some equivalent, you mean that's just the
Under
these are two are
under
isomorphic. So
this-
just call every few of AK. Just call it. So that's
Yes,
the same.
exactly. Yeah. So what is that? So this place is often denoted as phi infinity, and what is the corresponding valuation ring? All the elements in KT, the rational functions such that what? Right, so that phi infinity of Q, not infinity, which in terms of just all the over G such that G are polynomials with the F more. So and what is the valuation?
It's a notation. Phi infinity is a notation for all p's that phi of t is infinity. Right?
This.
You just not the like
Yeah, denoted by phi infinity.
just notation.
Just that. No.
Because the last time there's OP also notation.
So last time there were several for each monic irreducible P. There was a possible phi of P associated to it, and now in case 2 there is only one up to equivalence.
So just call it phi.
Exactly. It gives only one more place by infinity with this valuation ring, and what is the valuation? Exactly. So again, so like an element is in the valuation ring if its valuation is non-negative. So it's exactly like saying deg F minus deg G non-negative. Yeah, so okay, I want to define deg U is F over G. B, to avoid confusion, deg U is deg F minus deg G, what you would expect, and then deg U should be okay. And the valuation is minus deg U. Okay. So deg U, so an element is in O infinity if its valuation is greater than or equal to. And you can also see that this thing is an integer. So again, we need it when we claim that all the evaluations of the rational functions field are discrete. So here, the corresponding valuation V infinity is indeed the value is in the ordered group of the integer. Okay. So this completes the characterization of the places of the rational function fields. They are all of this form, and the residue field is always a finite extension of K. Here is the finite extension of the P. Here is just finite extension of degree 1. The residue field is just K. So this is in K. Okay. Questions?
And also the variations are always Z.
And all the valuations are discrete. Yeah.
What about if 1 is 0? Is mapped to 0? Just everything?
Sorry?
Is mapped to 0.
So it's just the first case. So if P is mapped to 0, then P should, then what is the corresponding P? Good. P. So you can check the proof and see that P, if phi of P is tau in L, then P of P is in fact the minimal polynomial of tau over. But you can try and. Okay, so now the second part. Okay, so the second part is as follows. So we have some field F and some valuation V from F to some order group gamma infinity. And then we can, by now we already know that we can associate the valuation ring of F, just the subring of F, all the functions, the elements of F, such that all the elements A in F, such that V of A is non-negative. And it has a, and what do we know about this ring?
We call it O of V.
Okay. So there is only one V. We are focusing on one V.
Fixed V, so then we call it
Good.
O of.
So we have a fixed F and a fixed V. And I use OF. It will be clear in a minute. But yes, it's the OV.
But generally, it depends on both V and F.
Right. So the valuation ring of this. So it's all the elements in F such that V of A is greater than or it's non-negative. So this is the ring, and this is a representative from the equivalence from the class of valuation. Just represent as some on 1V. And this is a local ring. It has a unique maximal ideal M of F. What is M? All the elements such that V of A is positive. Good. And what is the residue field? So if we take a corresponding place from F to L and infinity, then, so L, remember L can be large, but if we're only interested in the image of F inside L, without the infinity, then it is F bar, and it is just OF or MF. So this is a maximal ideal, so this is a field, and this is the residue field. The image of F in L without the infinity. So it's isomorphic to this portion. Okay, now, so far so good. And now we consider some subfield E. So what can we do? We can restrict this V to E and get a valuation from E. Gamma. So you can check, in fact, you checked in the lecture that the restriction is also a valuation. So it has a corresponding valuation ring of E. The valuation ring of this, all the elements in E, such that the restriction sends them to some non-negative thing. And what is OE in terms of this and this? Just the intersection, right? It's all the elements in E that are all both in E and in OF. and it has a maximal ideal ME, all the elements that their valuation is positive, and it is exactly the intersection of MF and OE. And what can you say about the residue field of this? So the place is just a restriction of phi to E. So the same way. And what is E? So this thing. So you saw in lecture that it's isomorphic to OE mod ME, and this thing can be embedded in OF mod MF, which is F bar. So you saw it in, I think, last lecture. So what I need you to remember that once we consider such a restriction, then the residue field E bar is isomorphic to this quotient, and we can think of it, and we will think of it as just a subfield of F bar. Okay. Now the lemma that we want to prove. Oh, and maybe one more word. What is the place if we take F bar to be this quotient? So we can take phi. Think of phi as take an element in F. If it is in OF, send it to its quotient modulo MF. Otherwise, send it to infinity. So the lemma which we will use that is the following. The product of two. Okay. So we have a E bar, a subfield of F bar. So F bar over E bar is a field extension, so it has some degree. This is called how it is called? Residual index. And we have one more index, which is now thinking of the valuations. Then F, well, 0 is mapped to infinity, and every element which is non-zero is mapped to some element in gamma. So the image is subgroup of gamma, V of F without 0. And we can also consider V of the restriction E. Maybe like this. So this is just the index of, so this is a subgroup group. This is a subgroup of this group. They are both subgroups of gamma. And this is just the index of this subgroup. And this is called the ramification index. And the lemma says that the product of the residual index and the ramification index is at most the degree of the extension F over E. So this is what we are going to prove. So is the statement clear? So we used it twice today. So in applications, we have some finite extension F of E. So F is a finite extension of E, say of degree n. So this is n. Then each one of them is at most n. So we use it twice today. So one time we knew that this was some finite number, and we induced that this was some finite number, and in some other time we use it to conclude that this is finite. So okay, so how can we prove it? So okay, so it might be less difficult than you think. So the idea is the following. So
About the
Yeah.
theorem, like, so the left part is like is an index as two fields
exactly.
cosets and stuff.
So this is a field extension, and this is a cosets.
This is the coset, sorry, and this is the field extension. So what
What is the dimension? The vector.
That's not appear there. This is a dimension, the degree of the field extension, f bar over e bar. This is also the dimension of the field extension, f bar over e. This is the index of this subgroup here.
Yes, just a reminder, I'm sorry for that.
Good. Okay.
So what is the dimension of the field extension? Maybe this is what I'm missing.
Good. So we can consider f bar as a vector space over this field. We will do it. Okay, so good. So that's what we'll do. So exactly. So what? So all right, and then explain. So let x1 to xm an element in OF be such that okay. So when I add bar, I mean an element in OF. Its bar is just its quotient. It's in this field, which is just its image under phi. And such that these M images are linearly independent over E bar. So if it's F bar is an extension of degree 5 of E bar, then we can take 5 elements in F bar, which are linearly independent over E bar. And what are the elements of F bar? They are just cosets in this ring, the residue field. So we can call them as the coset of x1, x2, up to xm, where the x's are in OF. Okay. So n can be as large as this index. So if it's finite, take m to be exactly this thing, and if it's infinite, so we can take n as large as we want. And now this one, so let y1 to yn. So what is this index? The index of the subgroup just means how many cosets, right? So if we have the index of G over H is the number of cosets of the form GH. Every coset is represented by some small g in G, so an element here. V of some y in F. So let's take some y1 to yn in F non-zero, such that their cosets, their images under the V y1 to vyn represent distinct cosets in the quotient. So remember, these two are subgroups of gamma, and gamma is abelian, so it's a normal subgroup. So it's just the so this is a group, not just the quotient group of this by this. So we can take if this index is n, we can find n elements in F non-zero, such that vy1 up to vyn represent distinct cosets in this quotient. And if it's infinite, then n can be as large as we want. So this is what we can work with. And the cool thing is it suffices us to show what suffices to show this. That if we take all the products I from 1 to m and j from 1 to n, then this is the subset of what? Of f, right? So every y is in f, and every x is in OF, and OF is contained in F.
Independent.
These elements are linearly independent over what? Over E. So it suffices to show that if we take all these products, then we get a linearly independent set over E. So suppose.
So why is it?
Oh, good. So if both are finite, n and m, so we can always take m, which is this, and n, which is this, and then we find m times n elements.
So you found like m times n elements in F.
In F, which are linearly independent over E. So this degree is at least m times n.
Yeah.
And if one of them is infinite, then again, so we can take m or n as large as we want. So this cannot be finite. So let's suppose that there is some linear with AJ in E, not all zeros. Okay. So take some non-trivial linear combination, and suppose that it's 0. And we will see that we'll get a contradiction. Okay. So for every j, there is I n and aij is constant. So right, so if for some j, all the coefficients aij for some j are all 0, so just omit this j to the summation. So with that, so claim the valuation of these things, and we for each j, valuation of this thing is the valuation, is the minimum of the aij. So this is the key claim. If we take these things, then for every j, the coefficient of yj, its valuation is this thing.
So the equality is this kind of right? And the inequality is supposed to be theta or something, or
So we will see.
but the quality matter, right?
Yeah. So fix J, sorry, and let's say be the be such that AKJ is the minimum. So, okay, so the minimum is it's K minimizes this thing. And what can we say about AKJ? Can it be 0? We assume that at least one of the AIJs is non-zero. So we V of this value is not infinity, so the minimal is finite, so it's not 0. So let's normalize. Let's find Bij, the Aij over AKJ. So this is an element in where? In E. This is in E, this is in E and non-zero. And what can we say about BKJ? 1. And in general, what can we say about the valuation of Bij? The valuation of Aij minus the valuation of AKJ. So it should be non-negative by definition of K as the minimum. Okay. So in other words, Bij belongs to the.
So like, why AKJ is not 0? How do you know?
We assume that there is some I such that Aij is non-zero, so its valuation is not infinity. So K should, and K is the minimum, so it should be finite. V of AKJ is finite, so it cannot be 0.
Ah, okay. AKJ is finite because just because it's the minimum finite.
Yeah.
Yeah. Okay.
So Bij belongs to the valuation ring OE because it's in E and its valuation is non-negative. And BKJ is 1, so it's not in ME, proper ideal. So what can we say about the, if we go mod ME, well, okay, so it's, of course, it's in, if it's in the valuation ring, then mod ME it's in E bar, and the KJ is non-zero. The fact that it's not in the ideal means that when we go modulo the ideal, it's not 0. Okay, so these are all elements in E bar, and remember that x1 to xn are, we chose in the beginning x1 to xn, which are in F bar, which are linearly independent over E bar. So if we consider this thing, okay, so I think I'll just today we'll just prove the claim and we'll complete the claim next time. So okay. Okay, so what can we say about this thing? These things belong to E bar. They are not all 0 because BKJ is non-zero. and these are linearly independent over E bar. So this is a non-trivial linear combination of the xi's over E bar, and these are linearly independent, so what can you say about it? Not zero. Good. By definition of xi. The xi bar are linearly independent over E bar. Good. So it follows that, what can we say about this sum?
This is not zero because it's sum of many, or zero but one, right?
Yeah, it's a non-trivial linear combination of these elements, which are linearly independent over E bar. So, right, if this was zero, then all the Bij, all the coefficients will have to be zero, but Bkj is not zero.
Looking at it, it's like Bij are the Bij are like the coefficients, and you say this is a non-trivial combination of xi's with xi's are independent.
Exactly. So this thing, so what can you say about this thing? So obviously, these are all in OF. These are all in OE, so also in OF, so obviously, and OF is a subring, so it's in OF. But when we go modulo MF, we get this thing, it's non-zero. So it's not in MF. So what is the valuation of this thing? Good, so it's in OF, so it's non-negative, but it's not in MF, so it's not positive, so it has to be zero. And we wanted to show this. So why? Okay, so now just if we use it with A, then just Aij is Bij is Aij and over A. I like to just Akj sum Bij xi, because just the way we define Bij is Aij over this. So it's the sum of the valuation, the Akj plus V of this. And V of this is zero. So it's just V of Akj, which what we wanted to show. Okay, so this proves the claim. Next time we will see it's 4 lines to exclude from this claim that the inequality that we want. Okay, so we'll continue next time. Question.